Okay, now let's consider some context to where we look at the data. Now, it isn't stressed in this particular standard, but it's always a good idea to do dot plots because that really gives you a much better handle of the nature of your data. So for example here, this is a nice set of data because there's no surprises. The mean and the median are going to be pretty representative, and in fact they're going to be pretty close to each other. Plus your interquartile range and your mean absolute deviation are going to be fairly small also because there's not much of a range. There's not a whole lot of variability here as far as your data. They're pretty closely packed together. So let's look at a context here. Let's suppose you're a teacher and you've given a test to your students and you have a class of 28. So there's 28 test grades. All right. So if I take these and I crunch out the numbers and I determine the average, the mean, that comes out to be 77.9. Then I make sure that my data is in order from least to greatest. I determine that the median was a 78 for my whole data set. And then for the upper and the lower halves, for the upper half, the median is 80. For the lower half, the median is 76. And so for those two values, I then take the difference between the two, which is 4. So my interquartile range is 4. Now, quite a bit of computation. Now I have to take all of my data points and figure out how far away each one of those is from the mean of 77.9. And when I do all that, I get a mean absolute deviation of 2.6. Then I do my box plot, and I've overlaid that with a dot plot to see the patterns as to where my values are. And notice that it's pretty condensed. It's pretty packed. The mean and the median are very close together, and my interquartile range and my mean absolute deviation values are pretty small. So it makes sense that the data looks like what it does. And even when as far as to determine the mild outlier fences, and in fact there are none, there just happens to be one data point, the 70, that is sort of on the borderline. It's exactly where the fence is. As a teacher, I would look at this and, well, the students did fairly well. Nobody really did poorly. But the highest grade was 85, so there really wasn't much on the upper end, but they are pretty closely packed together. So as a teacher, there's some pluses and minuses here. Now let's say you have that same class and you gave a second test. Still 28 students, but notice some of the differences in this data. Deliberately set it up to where the mean was exactly the same. The mean is 77.9 again. Our median is 84. Our values for the third and the first quartiles were 91 and 68, so our interquartile range is 23. And then again, we did all the number crunching. We took all of our individual data points and figured out how far away they are from 77.9, and we get a mean absolute deviation of 13.8. Now notice that even though the mean is the same, the data looks a lot different. This time the data is a lot more spread out. It's more dispersed. Notice that there is, some difference between the mean and the median, 84 versus 77.9. But the telltale values here are the interquartile range and the mean absolute deviation. Those are much larger than in the previous data set, which again parallels what the data looks like. Again, it is a lot more widely dispersed. In this case, there's a lot more at the upper end. So in this case, as a teacher, not too bad, although there were several students that did poorly. Let's take a third set of test grades. Again, 28 is the number of data points, but this time our mean is different. Now it's dropped to 70.4. Our median is 90, the halfway point between the 28 values. Our third and first quartile values are 97 and 41 for those two medians, which is a difference of 56. So that's our interquartile range. And then the average distance of all of our data points from the average of 70.4 is 28.3. Widely dispersed again, but this time notice that there's not very many values that are close to the mean. And there's a big difference between the mean and the median. And this time the data seems to be clustered at the two ends, at the upper end and at the lower end. So I guess this would be the results here tell us that the students either knew the topic very, very well, or they didn't know it hardly at all. So again, a little bit different data set here. And the telltale values are again the interquartile range and the mean absolute deviation. Those are very high values relative to the values of your data points. So the box plot and the dot plot also really help here to get a better handle on what the data looks like. Let's take a different context. Let's say you have 20 lions and all of the lions are weighed, and here's our data set in order from least to greatest. So we figured out that the average is 388, our median is 391, our median for the whole data set fell here, and so it falls halfway between 327 and 455, which is 391. Then for the medians of the upper and lower halves of the data, we get 481 and 293. That difference is 188, so our interquartile range is 188. And then when we figure out the average of the distances of all our data points from the 388, the mean absolute deviation is 90.9. This is sort of like that last data set for our third test grade. The data is widely dispersed and there's very few values close to the average, the median. There's very little difference between the mean and the median. And the data is clustered way over at the upper and lower ends. In statistics, this is often referred to as a bimodal distribution. So what could cause this? Well, from science we know that your male adult African lions are actually quite a bit bigger than your female adult lions. So that would be a very logical explanation for this, that we've actually got probably 10 female lions and 10 male adult lions, and that kind of explains the difference, why the data is clustered the way that it is. Let's take that data set for our lions and adjust it just a little bit. Let's say that we knock out the biggest of the male lions. Now look what that does to our data set. Okay, now we've got 19 values. Notice that there's very little difference between the mean absolute deviation. There's very little difference in the interquartile range. There really isn't a whole lot of difference in the average weight, 382.3 compared to 388. But look at the median, 391 versus 327. It shifted way over to the left. But notice why. Here, it just so happened that the median fell between, that expanse of numbers between the male and the female lion weights. But now, this shifted to the left, so now I'm at 327, which we would assume would probably be the heaviest of the female lions. So again, a big shift simply because of eliminating one of the male lions. So this is just an example of not to make assumptions as far as your mean and median and so forth, because again, just one slight difference in your data values can make a lot of difference, especially with something like your median. All it took was eliminating one of our data points and it made a whole lot of difference in where the median fell. Let's take another scenario, candy sales. Let's say you have 15 students that went out and sold a bunch of boxes of candy. Okay, and here's the values. Notice that almost all the kids sold anywhere from 1 to 5 boxes. But you got 2 kids that were way out here. One sold 68, another one sold 74 boxes. This data set is an example of what can happen when a set of values contains extreme outliers. Notice that the primary impact was on the mean and the mean absolute deviation. When we take the mean, it comes out to be 12. So it makes it look like our kids on average sold 12 boxes of candy each, when in fact most of them really sold closer to 2 or 3. So again, the extreme outliers made a big difference with the mean. Notice that the median is probably a lot closer to the actual values that we would expect, and you have a small interquartile range, 5 minus 2 being 3, but look at your mean absolute deviation. It comes out to 15.7. So what that's saying is that all of my data points are an average of 15.7 away from the mean, which really isn't, I mean, mathematically that's true, but when you look at your data, I said, wait a minute, most of my data points, the mean, are not that far. But again, it's the distance from the mean, not from the median. So in cases where you have extreme outliers, it really can make a big difference on some of your values, especially again on your mean and your mean absolute deviation. So to wrap up, here are some dot plots to kind of show what could happen in different contexts. And again, there's a whole lot of different contexts that you can make up as far as your data. So many real life scenarios that you can come up with. The data would probably be represented by one of these scenarios. You might have a scenario like this where there's not going to be a whole lot of surprises. What's going to happen there is that it's pretty condensed. There's not going to be much of a difference between your mean and your median. You're going to have fairly small values for your interquartile range and for your mean absolute deviation. The second set, as you can tell, is a lot more widely dispersed. So your mean and your median will probably be fairly close together, but you're going to have some large values for your mean absolute deviation and for your interquartile range, which again would give you the tip-off that there is a lot of variability in your data points. The third one is representative of what happened with the lions, that it is possible to have this kind of data. And in this case, your mean would definitely be misleading. And so again, that's why visual representations of your data, something like this, a dot plot, would really help to see what's really going on. And then another type of scenario or possibility would be this last one here. And this would be one where you